You can introduce Stefan or go?
That's the auditorium and a little tiny.
Huh? Do you want me to do it? Okay. Let's go. Okay.
Yes. No, it's not full.
I just call it music.
The music stand. Okay. The link is on the back of it. It picks up from the screen.
And how close are you?
Hello everyone, is this on? No, it's not. Hello. Welcome back from the break. We've got Stefan from Queen's University Belfast. He just graduated from there and he's just finished up an internship with Albemarle Orbital. He worked as thermal engineering. Yeah. Okay, so on to you.
Thank you, guys. Okay, so my presentation will be just about what I did for my final year project and what conclusions I found in regards to the actual relationship between the spin of the satellite and the thermal behavior of it. So I'll just get the mouse working in here. Okay, so the project I was working on was called, well, first of all, the Queen's University with the CubeSats could, in collaboration with University College Dublin, work on the Ireland's first satellite, the Ersat-1. We are all aware of what CubeSats are here, but just that as a research project, that was something that finally became possible so that even the smallest organizations could start playing around with space and space technologies. So the Ersat-1 is due to launch very soon. It's right now being assembled in the clean room, just sealed up for launch. And it had 3 different experimental modules. The sharpness of the image isn't very good with the projector, but if you look at the very top of that stack, there were 4 plates that had to be firmly isolated, and those 4 plates had 4 different types of paint and surface coating to basically do an environmental test and certify the paint for use in space. Now you can buy samples of that, and the last time I checked, it was like $500 for a tiny patch. The second payload was a gamma ray detector in a cube in the middle, just below the end plate, and then a magnetorquer incorporated into the rear of the solar panels. So 4 magnetorquers along the incorporated into the backside of the solar panels made by CloudSpace. So So the objectives of my project was just to look at this cube satellite, review and write about space, environments, become familiar with a thermal desktop, which is a plugin for Autodesk. It was developed for the ISS and larger applications, but it works just as fine for small satellites like CubeSats. And then I reproduced the model as a thermal model, developed, improved it, signed off with it, that's it, job done. So just did the standard methodology that you would for thermal engineering. Instead of looking at all the variations, you just do one worst case scenario for the hot case, one worst case scenario for the cold case, make sure that you're within spec for both environments, and comment on how accurate, and do analysis based on the certainty of your assumptions. So there are different improvements for this, where you see this is as the nodal model was made. So everything that you see here was modeled. There is the battery so it's radio on the bottom, battery, the board for power, then the data handling module, the module for the gamma ray detector, and the actual big blocky cube, which is the gamma ray detector. And then at the end, the yellow squares for just sensing for the environmental testing of the paint. And got the results. The results were all good. This is in degrees Kelvin, so you can see that you don't drop below 0, you don't rise above 50. You couldn't ask any more, so did 9 different cases. The only recommendation was just paint it white and it will work perfectly. Here you can see the actual heat distribution and the outside view of the solar panels along each one of the sides of this 2-unit CubeSat. So, in conclusion, everything was great. This was a very successful project. But then the lecturers at my university decided to do a Northern Irish specific satellite. This was the NERCSAT 1, which was supposed to be a Northern Ireland research satellite, and that was more of an aspirational project. The idea here was that you would have a large propulsion and a large optical module, and you would use it to investigate space debris, basically track space debris, and if necessary, then a second one in a constellation would come up and drag it down for re-entry. But this project had a lot of problems. First of all, there was not actually enough delta V to travel up and down between the debris and areas where the atmosphere would be able to actually catch and destroy it. And also the propulsion system. It was a Hall effect ion propulsion system that was being envisioned for this. It was creating too much heat in this small an area. So, I mean, this is only a 6-unit CubeSat. And it was to have all that heat for propulsion generated in the bottom. So if you look at the drawing on the right, the whole left side of the satellite, 1.5 units would be just batteries to provide the power for the plasma thruster. Those battery stack itself would create a high risk of overheating. So I was looking at what could be done to dissipate this heat, and just the surface area of that satellite was too small to effectively get rid of it. It would destroy the batteries it couldn't work. So I went back to the AirSat, the two-unit small research satellite for all of Ireland, and look at what all the different items of the hot and cold case, what was the individual effect of each item. So there was the color. The hottest case was with high solar activity, a steep angle, a high albedo of the Earth, a high infrared radiation of the Earth, and not spinning, and a black color. So then I changed each effect over, and found that the spin was having a remarkably large effect on the behavior of the satellite, despite the fact that existing literature would recommend that it shouldn't. Spinning a satellite should reduce the mean temperature, but not the overall temperature. Just move the maximum and the minimum closer to the mean, but not lower the actual mean temperature of the satellite. So the best article I found was by Mohammed Gadala. This is just the abstract, but I read through that paper, and I read through many different papers to see why is, for my simulation, spin behaving different than what existing literature recommends. And I found that their idealization of the interior of the satellite was pure conduction. And with the pure conduction on the inside of the satellite, yes, if you spin the satellite, the outer surfaces have a more equalized temperature. And if you would increase spin to infinity, the temperature distribution would be basically flat. But that's not how radiative transfer works on the inside of a satellite. So then what I found was that for my own analysis between a static case and a spun case, I was not only getting lower maximum, but also a lower minimum temperature of the orbit in the shadow. The mean temperature of the satellite was decreasing. So, I found that for that project, a 2-unit cube satellite could actively control its temperature using the onboard magnetorquers and varying its spin across the vertical z-axis. So if you think about the bottom of the antenna and the top with the environmental module alongside that axis spinning, you could vary the overall thermal behavior while still maintaining all the laws of physics of basically a thermal balance. The energy coming in equals the energy going out. I then repeated this simulation for higher rates of RPM, and found that yes, there is this relationship holds for different rates of RPM, where not only do you make the outer surfaces slightly cooler, and but you also have the minimum staying even, so that you have an overall temperature of the satellite staying lower as you increase the rate of RPM. So, well, so this initial investigation into what can be done to cool an overpowered aspirational satellite yielded the result that if you spin a satellite, it will be possible at no extra installation cost to have more onboard power and allow yourself to modify the temperatures on orbit without adding additional systems. Of course, then reducing the peak temperature of the outer solar panels, that should raise the efficiency of the solar panels and allow for more onboard power. And if you have a highly sensitive payload that has to have a constant temperature, you can, a set temperature to work with, you can slightly move the mean point up and down to match your what your payload requires. All right. So, in conclusion, if you have a satellite that overheats, try to experiment different things. First of all, painting a satellite white, it's a very easy way of making sure that it will actually work on orbit. The difference in paint is by far the biggest variation in the thermal behavior. And if you're finding that even with white paint your satellite keeps overheating, try something else, like seeing what would happen if you spin it. So just the message is that I would love to see someone put a induced spin into their satellite and record the temperature distribution of the satellite at different rates of spin and confirm my simulations for my final year project with Queens. So thank you for your attention, and do you have any questions?
Any questions for Stefan?
Please.
You mentioned painting the satellite white. You noticed that mine's black made out of it. Just from your expert opinion, am I in trouble?
It depends on mostly on your batteries. What kind of temperatures your batteries can handle. If it's more than 50 degrees, you probably will be in trouble. Sorry, if your batteries can't handle more than 50 degrees, you could be in trouble, yes. Okay. Second question. So in terms of analyzation, that's something that I was really trying to look into. Analyzation is a very complicated process and creates a very complex microstructure. So depending on the substrate, the concentrations of the solutions, the times, the temperatures, analyzation could give you anything. Any more questions?
Okay, thank you very much, Stefan. So next up we have Thomas, who's came over from Germany to be with us today. So known Thomas for some years. He used to go to Strathclyde University in sort of maybe a Glaswegian, pretending around Glaswegian. A little bit of a Ouija, a little bit not. But anyway, he's doing a startup now, and he's doing some really cool stuff out in Munich, and I'm sure you're really interested in talk, so you might.
Thank you very much, Tom. So actually, Alba Orbital helped us to also get our startup started with some LOIs. That's why we are quite happy that we are also being invited to the PocketQube workshop. And as Tom said, I was doing my PhD here in Strathclyde, just on the other side of the city. And that's why I always love to come back to Glasgow to visit all the places that I used to enjoy for 3 years while I was here. So I'm telling you a little bit about my startup, Deployables Cubed, and also how we can help you with thinking outside the PocketQube box, because we now go away from trying to be as small as possible, but being as big as you can be in space. So a little bit to us, we exist just since the beginning of the year, but we were able to already win some competitions. So here there was in July the InnoSpace Masters of ESA, OHB and Airbus with Alexander Gerst, the German astronaut, was there, and we were able to win the ESA competition, and that's why we are getting also a lot of traction right now, and we can do the things that we really like doing. We are right now 6 people, and just on Wednesday we received another grant, so we can expand more. So that's why I'm also mostly right now on my computer to get everything sorted. So we are located in Munich, actually not directly in Munich, but a small town outside Munich. It's called Oberpfaffenhofen or Gilching, where DLR and OHB is based. But there's also the ESA Business Incubation Center, which is supporting us as a startup, and we also get some expertise there. So yeah, when you're ever around in Munich, let me know, then I can show you around. So, but now why we are here and what we are doing. So here is a picture of the Unicorn 1. I thought we are in Glasgow, so I show a picture of Alba Orbiter. So the problem with the Cube satellite and PocketQube standard is that it's nice for preparing it for launching it. It's very small. You get cheap flights, relatively cheap flights, but in space you might want to have like bigger structures for big application. For example, like communication. Having bigger bandwidth, doing Earth observation, or maybe drag sails to then remove the space debris, also like deployable booms. So the thing around this limitation is the use of deployable. So here you quite nicely see the deployable solar cells and deployable antennas. But that's not what we are working on. We are working more on the more complex deployable structures, like these things here. So there's just a couple of examples. There's like also you can have inflatable space habitats, but we are more concentrating on the CubeSat application. So space habitats, not also space solar power. It's like concepts that are so far out, but we still need to consider them, because we also would like to use deployables there. Solar sails, drag sails for space debris removal, always a good application. And then the main business is antennas and reflectors, and that's where we can really support you. So all of us in the startup, we have been working in other industries for 5 to 10 years. And the idea to found our own company just came last year, when we had with our other company called HBS, we were developing a small drag sail, and we launched it on the Rocket Lab. It's business time rocket. So it was launched last year on the 11th of November from New Zealand. And they gave us 3 months to build a 1 kilogram payload. So we choose to go for a drag sail. We finished it the night before the flight to New Zealand. We took in our hand luggage and flew it down there. Met with Peter Beck, CEO of Rocket Lab, and then we put it on the kick stage, so it actually stayed on the kick stage. It was not deployed, so it's this small box in the center, so that's quite a famous picture. So every time when you see now that box, I hope you remember us. But a big issue that we had here is that we could not find a release device in time. So we looked at all around the world. We found frangibles from Tiny Aerospace. We found really big structures or big release devices from a European supplier, but none really for the PocketQube or the CubeSat market. So So we looked around. So there's like pyro cutters, there's like a pyro knife that cuts through the wire, or thermal knives, burn wire that you mostly use in PocketQubes or CubeSats, but we are thinking of application where you need more hold down power. So also there's different other release devices like Alchemia release nut, tiny aerospace, Frenchy bolts and pin pullers, but they are all ridiculously expensive, so they are all above $5,000. So if you also look at the Alchemia, if you want a flight model, it's like 16,000, but we don't want to pay that much, and we want to have a product for the market. So that's why we started designing our these devices, and we are right now in the third iteration. So I have the device with me. It's like really tiny. I can also give it around real quick. Let's see if I get it back at the end. So this is like a tiny, it's not a tiny, it's our release device. It's actually a pin puller that retracts the pin when a signal is given, and can be resetted over 100 times, and this can be preloaded with 100 newtons. So that's just the start, and we are looking at all different sizes because we are working right now on a patenting of this in a process. It can be used the same for a pin puller and a release nut. So that's just something that we are starting doing to have like an alternative for the tiny aerospace P5 device. But if you need any other sizes, just come up to me, because we are right now also starting to qualify it for space, and we can just change the size right now. So our idea is that at the end of this year we have a qualified device. Probably it will be January or February next year. So the application is release of solar arrays, release of deployable structures, but then there's also other application which is quite some traction. So that was at a small set, again with alpha orbital device. It's like the alpha pod, where you see all these silver release devices, and then on the top you see Tom's fingers with our release device on it. So that's also an application that we're considering of doing. But the thing is, as we all worked in deployables for so long, and also I did my PhD here on deployable space structures, that is where our real excitement lies. So we see the actuator more as the enabler, and then the deployable structures as the real exciting product. So that's what we are really working on right now, is to build these deployable structures. We already have 2 flying in space with on sounding rockets. It was a deployable helix antenna of 1 meter length, comes out of a 1U cube, and then also a drag sail mission. And we're thinking of having applications of also deployable appendices, where you can have a magnetometer or any instrument removed from the satellite. Then it's like next one would be Earth observation antennas, where you need a quite high gain antenna. That's what we are working on with partners, and also Internet of Things antennas, where you also need to have high gain for good communication, and also deep space communication. And then sales is where we started from, and that's where we are also still working on. But here it needs to be shown how the space debris mitigation guidelines get stronger. So that's really a business case. But if any one of you wants to fly a sail, we have that already ready. We give it to you for free. We just want to fly it. So with that, I'm come to my conclusion. So we are developing release devices specifically made for pico and nano satellites. So with having all the things in mind that are critical for these missions. So the cost needs to be very low, the size should be as small as possible, even smaller than that. And there should be no export limitation, because if you look at the devices of tiny aerospace, you have ITAR and other things. So we are right now collecting application for these kind of deployables and actuators. So if you have something for us, let us know. We can start the development right now, because we could help you to think outside the box. And with that, I'm through, and I open the floor for questions. You mean the pin pull or release nut? So it depends on the size, but we are aiming for between $500 and $2,000. So it's like a fourth of what you normally need to pay for American products. Because our idea came first from the direct sales, and here we wanted to also offer products to the customer, but if we then need to buy a 10,000 release device from other supplier, nobody will buy the product at the end.
Yeah, we have that problem.
Yeah.
Question on your sizing. This is a 26 by 26 by 25. That's an 8 wide volume and 1 mean. How small do you make this available?
So right now this size comes mainly from one of our first applications. It was for releasing solar arrays on a bigger cube satellite. So I think it's from a 12U cube. And that's especially that customer, they wanted to have a replacement for the P5 device. So that's why we started with this size, because we already had an application. But what is inside is what we patented and what we want to then can use in different sizes. So we think we can go down to a cubic centimeter. Lower than that, we have to see. We are probably getting too big with our fingers to assemble it. So theoretically, you can scale it down, but we just need to see how practical it is to redo it. But if you have an application, just let me know, and we try our best to make it as small as possible. So that's where we want to have it qualified. So we are right now in the third prototype iteration state, where we still optimize the design, and then the idea would be in October that we just go for test campaign. So we have a couple of our colleagues sitting in front of the vacuum chamber and resetting this thing 1,000 times. So it's not me, it will be someone else.
Any more questions or comments? Give them a round of applause. Very exciting talk. So we're getting close to the end now. So we come forward, Azar. So Azar, we've worked together for 4 years now. Yeah. So Azar is a bit of a radio genius. He's sort of see it. He's been doing RF for. It's only I've been alive for the place.
27 years.
27 years, so nearly. So yeah, what is artists know about radios isn't worth it, I don't think. So hopefully
It's always something worth it.
hopefully we can drop you guys some knowledge on that, and yeah, we can tell you about some of the developments we've been doing on the outbound radios, and yeah, just like the mix here. So
Great. Hi guys. Good evening, I guess, almost. Thank you very much, first of all, for the invitation to come and present here. Thanks, Tom. I've been working with Tom, as Tom mentioned, for maybe over 4 years now. 4 years ago, I got a call from Tom. Listen, we're doing this little satellite, and we need some radio help, and you're a local guy. What can you do for us? And I just wasn't excited. I really got me very, very interested in just the size of the satellite that was involved. Of course, I worked on radio systems for cellular communications, very high power stuff, some space stuff, but the bigger stuff. So this was quite interesting. And so I was very interested in taking up the challenge. And the first challenge that we had was to put together a radio that will communicate from a LEO orbit to a GEO orbit. Now, the challenges involved in that, first of all, obviously, LEO orbit, you got roughly 90 minutes orbit time. GEO orbits, satellites are stationary. It was a geostationary satellite that we were to communicate with. And it was a proof of concept to build a radio that could listen to some data and communicate to a geostationary satellite, which would relay back to Earth. So as you can imagine, from low Earth orbit, roughly 450 kilometer altitude, to geostationary, nearly 37,000 kilometers away, there's 190 degrees path loss involved in that. It's not your regular radio surround. So how do we make it happen in a PocketQube size radio? So that was a challenge. So the challenge was that obviously, because of the size of the radio, the power limitations were there. And we also had this requirement to do a proof of concept of using LoRa. So one of the reasons why you might have heard of LoRa a number of times in this workshop and also previously. LoRa is a modulation standard. It's proprietary to Semtech Corporation, but it's the Internet of Things being a new buzz industry, particularly 4 or 6 years ago. It was in its early days. So there was a lot of hype around the IoT market, and one of the concepts was to use the IoT technologies for space. And so LoRa was kind of fitting into that the whole story, the PocketQube story. And for that radio, we did actually make it work. Sadly, our geostationary partner kind of fell away in the story, in the project. So we never actually got to test in orbit whether the whole concept will work. But we designed it to work. To make it work, it was necessary to use LoRa modulation. Standard normal GFSK, MSK modulation just wouldn't work, simply because of the signal requirements. So we did show that it would work, but it would only work with very low data rates. For sensing applications, which might be useful, but as a proof of concept, we actually showed what the limitations were. And also in that process, ESA did some measurements, because one of the big parameters which affect radio performance is Doppler, of course, and for the satellites, LEO satellites, Doppler is a big problem. And so, would LoRa be able to handle the Doppler shifts that we would experience? Now, so as I said, there's 190 dBs of path loss, but there's also the Doppler parameters in there. Now that geostationary satellite was fortunately just a bent pipe, which means that if it receives a signal, it converts it to a different frequency and beams that back down to Earth. Now, that particular geostationary satellite was using Ka band 4, which is much higher frequency, which means that the link closure, they're using large dishes, high gain antennas. They had a traveling wave tube amplifier in the radio in the satellite, so they had all the parameters available to link back down to Earth. So we simply had to make it work from LEO to GEO, and we did it. We did it, but we couldn't prove it. So we think we did it, but we couldn't prove it. Okay. So the next thing was, what the parameters, what the issues that we came up against. So one of the parameters we had to work within was the size. So the 5 centimeter square is quite a small size, but it's not impossible to make radios. radios have been made much smaller than that. You can actually buy little transceivers, single chip transceivers. But the challenge here was to make it operate in the S-band at 2.25 gigahertz. And there is nothing on the market that's targeted for that frequency band. So we have to take something else and make it work for that. So to do it in that small space of the 5 centimeter cube square of the area available, when you take into account, as you have experienced yourselves, the connector, the voltage connector occupies a lot of space. Then you've got your digital communication stuff, which occupies space. So the space available for the radio to function in is quite small. But when you have to add in the frequency translation to make it work for the 2.25 gigahertz, it becomes a bigger challenge. And that was one of the issues that we had. Make it work in low power. Of course, PocketQube satellites, you're limited to how much power that's available for you. And so the maximum power that we could sustain at that time was 1 watt transmission. We had a radio designed for 2 watts, but the intention was to back it off to operate at 1 watt so that we can drain the battery significantly. That's for transmit. And of course, for receive, these radios are actually quite low power, so they can continue operation for a long time. And low cost. Low cost parameter means that you have to use commercial off-the-shelf components, Fox components. And the best trend we have in this is the IoT market. IoT is a low cost market. IoT has already crossed the bridge in terms of the modems and the transceivers for highly integrated radios. So it's natural. It's natural that we should just pick what they have done and make it work for space applications. And that's what it's effectively what we did. We simply took an IoT component and put some frequency translation in there. Now, when you do frequency translation, you also have the issues of spurious transmissions, spurious frequencies that you generate. And then, of course, going to S-band to 2.25 gigahertz, those radios that were designed for up to 1 gigahertz, the Doppler frequencies that they were designed to handle, those parameters shift and become more difficult in the S-band. So we were right on the limit of the radios being able to work, but we wish we'd actually showed you actual numbers, actual performance. But our geostationary partner, unfortunately, backed away from the project. So as I mentioned, LoRa is long range Semtex implementation of a modulation scheme known as chirp spread spectrum. Without going into too much technical detail, when you want to transmit data over radio, you have to encode the information onto the radio signal, modulate it. So a number of ways of doing it, and spread spectrum is one method out of many. So with a carrier, the radio frequency carrier, you can modulate the amplitude, the phase, and the frequency. And what LoRa does is a special form of higher bit rate. You spread the signal by making it clock faster. You send the data much faster. So it's not redundancy built in, but it spreads the signal. Making higher bit rate signal spreads the energy into a wider spectrum. And it also does a time domain chirp of the carrier. So the net effect is that you actually can send a signal of a greater distance. So we're trying to not go into too much technical detail, but you can send a signal of a greater distance and detect it. So that's the kind of benefit of it. For the IoT market, of course, it means you can build low power radios and be able to communicate over longer distances. So that's why it's popular, basically. So I've gone through that. In fact, I won't go through too much details of the actual modulation format, but the one thing I would mention to you for the satellites that you guys are building, when you have a rapid change in frequency, you're using FSK modulation, for example, for communications. Any rapid change in your signal will inevitably cause a large generation of spurious frequency. So in order to reduce those spurious emissions, we have to make those transitions as smooth as possible. So in normal FSK, MSK modulation formats get filtered so that the transitions become smoother. So the difference between a GFSK signal and a FSK signal is simply because that transition has been filtered to make it smoother. When you make it smoother transition, the spurious emissions become much smaller, and that's the whole reason for doing it. So in chirp spectrum, you do deliberate broadband modulation, but you also do it in the time domain. You chirp signal, which basically means in the time. I've got some plots I'd like to show you. There we go. So a profile of the spectrum of an MSK signal and a filtered MSK signal. So the reason why this makes a difference is that when you are applying for licenses for your satellites, for your radios, you have to meet some requirements. If you are given 100 kilohertz spectrum, license for 100 kilohertz spectrum, you have to meet some parameters for your neighbors. Right? So there's the maximum power that you can transmit in your neighboring spectrum is limited. It's actually mandated in the radio regulations, the World Radio Regulations document, ITU document. So there is a reason for filtering. So the difference between MSK and GMSK, as you can see on there, is quite substantial when you go further out into the spectrum, further away from your carrier, from your baseband signal. And that's important. So for a LoRa modulation, what that does, so it's actually difficult to represent what actually LoRa modulation does. Okay, so what these plots actually showing is effectively, if you look at the green line at the top, that's the spectrum. So you have a spectral view, and then a time domain view coming down. This is your typical waterfall plot. The signal in the time domain, as you can see, is shifting, and the data is modulated in the time domain. So you have not only a spread spectrum, but the center frequency of the spectrum shifts in time. And that shift is what carries the information. Now the reason for doing it is because it helps us to manage the recovery of the signal. We can actually sense that shift much more in a much weaker signal than any other method of modulation. So LoRa is gaining a lot of traction in the IoT market for that reason. So, like I said, at 2.25 gigahertz, where we have to operate, there was nothing in the market that could operate directly at 2.25 gigahertz. There are ICs, there are transceivers that operate up to roughly 1 gigahertz. So from 150 megahertz to 1 gigahertz, there are ready-made solutions. If you're operating in the UHF band, you've got a very highly integrated transceiver you can take and make a very small radio directly. And we have done that. But when you're operating outside that band, unless you are operating in the 2.4 to 2.5 gigahertz band, anywhere else, you have to take a standard component and convert the frequency, which means you need a synthesizer, which means you need a mixer, which means you need filters, and you need a separate PA. So all of that can add cost, adds power, adds complexity to the radio, and takes up space. So these are the first radios that we implemented, which we're ready to fly. So these take a standard 1 gigahertz transceiver, LoRa transceiver, and convert the frequency to 2.25 gigahertz. Now, one of the problems we have is, like I said, the spurious emissions. and we had picked frequencies to use that would minimize spurious emissions. And today what we have done is, we actually ditched that radio, but this was the first radio which was ready to fly from the Leo to geo communications. Never got to actually test it, but this radio, this is our latest one that we've designed for the other bands. That uses a LoRa transceiver. The extra component you see is simply because we do translation. There's a lot of filtering going on there, just to manage the spurious emissions. But we have managed to achieve data sheet sensitivities. So the data sheet numbers that they quote in the LoRa specifications, we have managed to achieve those sensitivity numbers, which means that actually our sensitivity is good enough that we can close the link at a decent data rate from Leo back to Earth. The big problem is trying to get the data down fast enough. And of course, at S-band, one of the parameters that you guys, if you haven't come across them already, is that the maximum power you can transmit, there is a requirement for the maximum power density received at the Earth. Okay. And it's a quite a small number, but it limits how much power you can transmit from the lower orbit. That then sets a level of the maximum power that maximum signal to the ratio that you can receive at the Earth. The only way around it is to use an antenna with a high gain at the Earth. Okay. You have no other parameter available to you to be able to either increase the power, or because even if you use a narrow beam antenna on the satellite, you still have to meet the requirement for the maximum power density at the Earth's surface. And that's mandated in the World Radio regulations. So the only way around it is to use a high gain antenna at the Earth. And that's important because it depends on what your data rate requirements are. If you want to bring data down at megabits per second, you really need a big dish. But for typical 9.6 kilobits per second for telemetry data, this radio for the power level it transmits achieve the sensitivity numbers that it's achieving, that will close that link, no problem. So you will see if you in the other room. This radio, I think, is in the shields in the other room, so you can actually see that. This radio achieves the sensitivities, transmits 1 watt power, up to 1 watt power, and it will allow you to certainly close the link with a very good data rate. We have been working with this at 250 to 200 odd kilobits per second, and it works fantastically well. So the point is that you can take commercial off-the-shelf components, you can build radios which will meet your size requirements for the PocketQube, your power requirements, and the cost targets. So we have done it, it is possible, and I'm sure there's a number of other companies that have actually achieved it as well. But our requirement was to work with the S-band. So we can tune anywhere from 2.2 gigahertz to 2.6. In fact, tunability is anywhere up to 2.8 gigahertz. But we deliberately limit the actual usable bandwidth is for filtering reasons to make the experience issues in practice. So that's really everything I have to say. I just wanted to mention that same radio with fewer components, of course, so we're not doing a transition. UHF frequencies up to 1 gigahertz even, the radio becomes very, very small. And we have tested both at UHF and S-band. We have achieved the full sensitivity the full sensitivity numbers that Semtech quote in their data. So, take any questions. Yes. So Tom is the one to speak to. But we have the radio. The radio is ready to fly, and in fact we are looking forward to flying them very soon. So and they are available. And a lot of what we do is there and is available for purchase for anybody. Tom, this was developed for Alba and Alba other guys. But yes, you can actually buy it. Yes. So we use the SX 1286. Sorry, SX 1286. We looked at several of the Semtech solutions, and really the frequency requirements for really important. We're operating this with a version which goes up to 1 gigahertz, but we fixed the frequency for the SX. So the IF frequency is fixed, and we have a synthesizer which then converts, which feeds a mixer that converts the fixed IF up to anywhere in the S band. Now the big problem is with heat out of the deep space network frequency. So everything else, the spurious emissions, it meets the target for everything else. But for the deep space network, it's really what we need to avoid. So we can choose combinations of the IF and the mixer synthesizer frequencies to keep away from the DSN frequency. So DSN, anywhere close to DSN, NASA will tell you turn it off. So don't work anyway. Don't upset NASA. That's kind of key lesson. Okay, thank you very much.
Well, we've nearly made it. Thanks, Cesar, again for coming so long. We appreciate it. So yeah, I'm the final talk, so I'm between you and the exit, so hopefully it won't be too bad. Hopefully it won't be too much overlap with the other speakers, but see how it goes. I just need to know if you can back this time. Just bear with us for a few minutes. Send this to you, right?
on the one like that.
That's better than what we're going to get, I think. This one?
I was on second screen and you're definitely going to get the optimal resolution for that. Even when it turns off.
Okay, let's do that then.
You get the perfect resolution for that monitor. So everything will fit.
Hello. So yeah. So hi, I'm Tom Walkinshaw. I've probably met you before. If not, I run a company called Alba Orbital. We are big into PocketQubes at Alba and really keen to get more people into the field and doing more cool stuff in space at low cost and hopefully capabilities. Constantine, I think, had this slide up earlier on, but worth a year today to the point of the company, I guess, given the location and the venue. So we want to advance the PocketQube cause and advance monetization. Our goal is to be the best PocketQube in the world and for that to matter. So there's no point just Alba existing and no other companies existing. We want to see an ecosystem. We want to see lots of great PocketQube teams. If you look at the companies, ultimately, if you look at the CubeSat world, obviously there's a lot of public listed companies now, and they're all very big, successful, mature companies relative to where they were 10, 15 years ago. And Alba has obviously been doing this probably longer than anyone in terms of being a company and man hours and man years, man decades, whatever, on the PocketQube stuff. And we're trying to encourage an ecosystem because that's what it takes to make these things happen. You know, it's not one team, it's not one company, it takes a community, you know, it's a village. So that's what Alba's all about. It's the 3-stage master plan. So stage 1 and 2 are kind of very public. I'll talk about them. Stage 3 is not very well defined at this stage, so I'll just focus on what's relevant. And really, stage 1 is probably the most relevant for the community. So really, this somewhat maybe came after the fact when we realised what the problems were in terms of getting PocketQubes to space. But ultimately, stage 1 launched PocketQubes. We procured a launch a number of years ago from another PocketQube launch vendor, and sadly hasn't moved very far from the shelf, unfortunately. So we realised that the problem was the launch access, and even if it's really cheap, you know, it's a lot cheaper than the CubeSat say. If the thing doesn't launch, then you know it's not that cheap, you know, and we need to get things going there. Stage 2, platforms. So we've had Unicorn 1 already, and I think there's been a bunch of slides with Unicorn 1 on it. Unicorn 2 obviously is our new platform, and in the future there'll be a Unicorn 3, there'll be a Unicorn 4 as well. Currently there's no plans on Unicorn 3. We have some sort of baseline specs that I've shared with the engineering team about targets, but as of just now, we're mostly focusing on Unicorn production ramp and trying to make that really solid for the customers we have there. And stage 3, I mean, I think the reality is what we're doing is going to enable new businesses to exist in the world, and ultimately the end game there is constellations. Can you provide a service to people for less? Can you produce a service that's currently not feasible because you need too many satellites or too many nodes in your network to make it viable today? That's really the big challenge, right? So that's the sort of 3-stage plan that we have at Alba. We're trying to sort of get out a video up with some vibration testing.
I can get the video up.
Yeah, got it?
Okay.
Cool. So this is AlbaPod, so you've probably already seen it. This is V2, so without sort of duplicating too much what's previously happened, V2 is a lot better than V1. It's, I think, 63% lighter, which is really one of the core metrics when you're looking at deployer design. You want it to be really light, and why do you guys care, right? You guys don't buy pods, right? You guys buy launches, right? Well, the reality is we need to make the economics work. If the pod weighs the same as the satellites, if that's a mass fraction of 1 to 1, we have to buy a kilogram for every PocketQube, for every kilogram of PocketQubes we fly, which means, you know, we're going to have to charge more, or we're not going to make any money. And if we don't make any money, there's not going to be any launches because there will be no companies. So it's really important to make the economics add up. And I think with AlphaPod V2, we're getting there on the price to run it economically. Obviously, it depends how much you're paying your kilograms for, and that market's very turbulent just now, and hopefully it's going to end up in a nice place. But we've been working on that quite well. Good job, everybody. This is some of our vibe testing we've been doing. So this is like a week ago we've done this over in the Higgs Centre, so they're one of the exhibitors. Essentially, this class 10,000 clean room, putting AlphaPod V2 through its paces. This is actually the second round of AlphaPod V2 testing. V1 was pretty spectacularly bad, as we figured out that it can take pretty extreme loads, but we obviously had to do a proper qualification, and that's what we've been up to on the V2. So they're really good guys, and I'm just listening. So yeah, so that's pretty good video. So yes, that's it mounted up on the display. So we've done custom jig for that. The cool thing about that jig, if you're interested, jigs aren't interested in that, they're that interested, but it can actually fit different vibe tables, which is a big deal, because it turns out that the spacing on vibe tables is different, and there's 2 vibe tables in Edinburgh that use different spacing, one's in inches and one's in metric, and you know, it's not great. But anyway, that's quite nifty design. Here's it with more instrumentation. I mean, all pretty good. You can chat to the Met guys if you want to know more. This was a picture from our original test that we done, must have been about 3 or 4 months ago on AlphaPod V2. So that was our first test. Since then, we've done a bunch of upgrades. We've got redundant limit switches on both the door and the pusher plate, which means that when the PocketQubes start moving, we'll know that the pusher plate is moving, but the fact that we got a high-low signal on that. The door open, we have limit switches on that as well. So the idea is to try and get as much data out of the pod as possible, because we want to know what's going on up there as much as we can, even though we're somewhat blind in many ways. And in the background, actually, you can see one of our customer satellites that's also getting qualified. So that's Tracy, which is the guy who built Ren. So he's flying with us. So we're doing the integration for Alpha Cluster 2 on Monday for Pod 1, which would be really cool. So you've probably seen the 96p as well. I guess the question is, why build a 96p if there's not 96 PocketQubes? And I guess the assumption is there that we hope that there will be enough demand at some point that the 96p makes sense. And for us, we want to show that constellations of PocketQubes aren't crazy chat, that they're really important to the future of the community, and that we can build the infrastructure today to support startups, to support science, to support outreach, and to make the economics work. If we can get to economies of scale, then we can really do cool stuff, and we can be super competitive on what we charge people per launch slot. So yeah, so actually, we don't have the video, but 96p, we had to have a crane to move 96p, it's just ridiculous. So all in, I think we're about 44 kilograms when that thing's fully loaded, which is a lot of PocketQubes. We think we can have better mass fraction on that. That's a very unoptimized V1, but it's totally doable, and we'll be really excited to fly that in the next couple of years, hopefully. We'll always get this picture, but yeah, essentially on Monday, 9th December, we're integrating the first 4 out of 5 PocketQubes. So we've got Julian's satellite, Fuzza. What's that? You're all about Fuzza. We've got ATL1, which is ATL1 and Smog P from Hungary, the Hungarian team. So they're coming in to Glasgow on Monday. We've got Tracy coming in Sunday night, I believe. So we'll have 4, and then eventually we're going to get Joe as well when he's ready to go, hopefully in the next few weeks. So I guess this is what you guys mostly would be interested in this presentation. This is sort of the high-level stuff for Cluster 1. I mean, Cluster 1's turned into a bit of a disappointment, to be honest, in the sense that Vector obviously have been having their difficulties, and you know, we got a sort of yeah, it's pretty tricky. What to say about that? I mean, obviously they were here last year. They had a lot of money, they had a lot of resources, and for whatever reason, it didn't quite work out there. So we're looking at options to see what we can do there. We're going to see what emerges with Vector, and then look around on that, and that's is what it is. But yeah, Cluster 2 looks like it's going to be the first one to fly. That's integrating next week in Glasgow and Sweden. The interesting thing is we're sold out the first 2. We have some space in Cluster 3, but that's going pretty quick. So if you want to fly something next year, then don't delay and all that. And really, the plan for 96P would be a Cluster 4 launch potentially. I mean, that's probably the earliest. It really depends on the demand. Sort of Cluster 4, Cluster 5 is probably when it's likely to debut, assuming that the market sort of grows with sort of reasonable expectations and the first constellation gets funded. I don't know if you can read that. Sorry. Oh, good. So yeah, so this is the album manifest. It was the current version that we have, I think. It's more up to date on the website actually. So we've got Cluster 1 and Cluster 2. Cool thing with Cluster 2, we went to 400 km Sunset Corbett with Rocket Lab. Rocket Lab guys are really cool. Obviously they've flown I think 7-8 times now. You know, we've been working with them for some time now, and it was really great to get the community involved with Rocket Lab, given that they've got a really solid record now of flight heritage. They've been signed up, I think they've launched like once or twice, so we've really been fortunate to work with those guys, and they're really been grateful, and hopefully they'll be the guys that allow us to get to orbit for the community for the first time in like 6 years or something crazy, and you know, hopefully we can end the drought on the launches. Cluster 3, so we've got 4 customers on that now. I think we've announced 2, maybe 3 now, so ESAT's joined that. So that's really exciting to be working with Oriole on the team. We've got PocketQube from Tokyo, Japan. So they're the first Asian PocketQube to be manifested, so it's great that the community is growing. We have Ruju 260A from Turkey, who are a 1P. Unfortunately, they couldn't make it. I think some P's are a really good thing, but they're really keen, and they're trying to get the program going out in Turkey, which is really awesome. They're manifested. We've got 7 satellites for Cluster 2, ATL, Tracy, Discovery, Smog, Fonza, and I'll talk a little bit more about NOR1A, NOR1B. So that's the name that our customer startup has given to their unicorns. So the unicorn naming thing is we have our internal name, and then the customer has their name, and they're both right. We just tend to use different names and numbers and things. Pricing, we list our pricing publicly, which is pretty unusual for launch brokers. So we're 25k for 1P, 60k for 3P, and then sort of halfway between for 2P. And I think that's important because you want to close business cases, right? So if you have to kind of inquire and guess, then it's not good. And that's actually the cheapest price in the world for a satellite launch, by the way, on a flight from a rocket. So this is what Cluster 2 Pod 1 looks like, or would kind of look like, I guess, sort of different quality of CADs we got from the team. We get some people have really high res CADs, and we get people who maybe don't really CAD their satellite, and you know, it's all cool. There's no requirement to have pretty CADs, but it certainly helps when you do digital fit checks if you have something that resembles what you're building. But not a requirement, just nice to have, obviously. Shots and stuff. So, in terms of the order, there won't probably be this order. It may actually be this order. Yeah. So the ATL, 2P, then Fozza, then Smog, then probably Tracy, then Joe. So yeah, we're still playing around with the order. At some point we'll probably put in a simulation of what happens when these things deploy, and the reason for the debate this morning is to try and maybe get the conversation going to a place where bad things don't happen. It's kind of like a loop-to-loop freight train. If you've ever seen Starlink, but just imagine that thing doing loops through the sky. That's pretty much in the old Clyde. It's pretty much, unfortunately, the state of play on PocketQube today. It's really well to kind of clean up in the standards. Obviously, everyone had already built their satellite, and retrofits are not the easiest thing to do, and everyone has different shapes and different faces and different things in each face. So cluster 3, hopefully we'll be able to agree on some stuff that will avoid any major issues, and then as we refine it, we'll get something really slick. So this is Alba, Alba 2018. So hopefully some of you guys have been able to come visit Alba. If not, I'll be at the office tomorrow at 1 o'clock. If anybody wants to stop by, just shoot me an email or reach out to someone at Alba and let me know. Give me a heads up, whatever, from my mobile or put me on Facebook, whatever, just let me know. So I'll be at the office from 1 to maybe 2. We've got some battery day being Irene, so it'll be fun. So yeah, the cool thing about the lab now is we actually, sort of accused by some of my team of not spending money on things. But I spent quite a lot of money on my setup. Got class 10,000 clean room, so everything's really clean. You see the dust on top of the clean room. It's insane to think like, you look inside and you say, oh, it's clean, that's great. You look on the roof and you're cakes of dust. So it really does work, that thing. And really important when you're doing your solar panels. Obviously, you want to keep them as clean as possible. If you're doing optics, you want to keep them clean. And I think in general, we want to try and, while we never force it on anyone to build stuff in your clean rooms, obviously we want things to work, and we want to follow decent good practice of how to build things. So we do all our integrations in that clean room now, so that's where we're going to be holding cluster 2 integration on Monday. So that'll be really exciting. We have a handful cage as well now here that we built. So those of you who came to the open house on Wednesday, those of you who have been at Alba before, you see the Helms Home cage that we've built. I've got an airbag table in there, so you do the ECS testing, really useful tools. Got a lot of RF equipment for Zara and Andy, so there's lots of good toys in there now. So if you get the chance to come out and visit, please do. And we're really welcome to tours and stuff, so just head up. So these are fairly historic satellites. Another one on the left, that's just like a prototype. But these two satellites, this is Unicorn 2B and 2C, or rather the wings of that chassis. We haven't actually built all the back planes in this particular stage of the build. You kind of get the idea of what we're trying to do. Unicorn has big wings, can generate about 20 watt peak power with temperature. Four unicorns in the clean room is quite nice. So you probably double that, got Alba Pod up in the background as well. So really the game plan is to be knocking these things out once a month. That's kind of the internal Alba target for production. And we think that is totally doable. Andy assures me that's totally doable. And we're going to do that. Easy. Here's some cool cards I found on PC. Basically, we've got Unicorn 2A configuration. So we actually redesigned it so the hatch opens from the bottom, which is quite a big deal in the systems level design here. And stowed, so while you see a unicorn with the big wings, and that's really cool, generates a lot of power, actually we fold all that up, so that's how we can fit it into Alba pods. And in general, Alba's fairly keen on deployables. We don't allow drag deployables in the pods simply because we worry about jamming risk. So it only takes one team to jam the pod and ruin it for everyone. So see one of the satellites at the front of one of the pods and there's 5-6 PocketQubes in it jams up. It's a bad day for everyone. So constrain your deployables, please, if you're thinking deployables, but don't be discouraged. We're really keen to do deployables. And deployables make PocketQubes a lot better, allow us to do cooler missions and improve the community and get more people psyched up for PocketQubes. So yes, we've been doing some testing in Unicorn 2. Actually got Tracy in here as well, so some Paul satellites have performed really well, Tracy on the bike table. We did bike test in Unicorn 2. think we'll be doing some flight testing in the next few weeks as well on that when we get the 2B flight build done. So that's all very exciting. And that's the stock configuration as well. So we've got some sensors on the top, solar panelings. That's not got a payload in that one, but it's got actuators in there as well. TVAC, very important. So we've done a TVAC cycle as well on Unicorn 2. So we done that through in Edinburgh. I mean, TVAC cycle's not really mandatory, it's mostly bakeout's mandatory. We actually have Alpha Pod V2, Pod 1 Cluster 2 currently on bakeout, actually across the campus, part of Glasgow, so that's a flight pod's currently being baking out. Cycling's quite important, obviously, if you want to characterise your platform, make sure that you know what's going on in there. Pricey testing, it's up to you if you want to do it, but you absolutely have to do bakeout. I'm not sure if that shows up, so that was very bright. That's Unicorn 2A, or at least part of an early build of 2A. So we have the camera lens in there. Unicorn 2 is basically designed around the camera payloads. I mean, I'm really a big believer of one of the killer apps of PocketQubes will be a lot of EO-based payloads. So image of the Earth, unique ways, really high temporal resolution, that sort of thing. Actually, half the satellite in Unicorn can be used for payload, so we can fit a nice big camera there. And that sort of camera lens there, so that would be a 70mm focal length camera. So it's very similar to the one that GomSpace use on their Nano Eye product. It's just got a heritage, and I think it's got a 42mm aperture. Ground resolution, I believe, is 400 is about 16 meters per pixel, so 1616. So fairly good. I think we're 500, we're about 22 meters. So you're actually pulling off fairly good imagery. Often one of the sort of criticisms of PocketQubes is small apertures, bad ground sampling distance. So we've got a customer now for B and C. So we're actually nearly done B and C. So a company called Staraspace, who unfortunately I can't be here today. They're very busy doing fundraising, I believe. So they've really been a massive support to Alba and a big believer in the concept and what we're trying to do. So for background, Stara are essentially a US tech startup who are very keen to do a network in space for other people to relay their data back via a constellation of PocketQubes. So ISLs between hundreds of satellites. Essentially, you get a module on your satellite, and then they would get that data back to you, and then subscription, a bit like the ground station network, like Sean stuff or some of the other people. So that's really cool. So Tyler, at the top left there, defense, one of our engineers, is the co-founder, and there's also another co-founder who is a billionaire. It was pretty cool. From Uber, called Shiv Peshwar. And one of the engineers, Costa, who's been putting together a ground station, and they're using one of the Alba radios there to do some ground station testing. So they have a really nice ground station setup. We've just got some funding to do our ground stations, so we're building up a movable ground station, which would be S-band and UHF. So that's something I think Tony's been working on at Alba. And I mean, it won't look exactly like theirs, but they had very similar specs to what we were planning and stuff. We shared a lot of ideas and sort of input on the ground station. And they're based out in, I think it's North Carolina. So if anybody ever wants to go check it out, it's in the middle of nowhere, so it's pretty cool. Yeah, I've not got a lot of text in my slides, so I'll try and just get you pictures of cool stuff. Like I say, we're shooting for 1-to-1 production rate, really for the Unicorn customers, and I would say the Unicorn customers are more kind of VC-backed startups, that sort of world. People, it's not as cheap to do a unicorn. I mean, they're professionally engineered, and we've got a lot of engineers and costs and overhead and things. But it's a really nice system. So we're shooting for 1 a month production rate, which I think seems to be doable. And beyond 1 a month, I think once we start to get good at that, we're going to try and ramp it. Obviously, and the cool thing about Unicorn is, unlike a CubeSat manufacturer who does a 1U design, a 2U design, a 3U design, a 6U design, a 12U design, we have one design basically, or one form factor. We only build 3 Ps for Unicorn, you know, I think for me that's really important because that should hopefully allow us to ramp production. And yeah, in terms of quotes, we've got a number of quotes for people to purchase E and F. So I think we're quite close with some of them from D, and some of the others. And E and F, people's quotes in there, so we're quite confident that that will get sort of sold in the next few weeks or so. So quite exciting. Yeah, that's the plan, right? So hopefully in a few months from now we'll have 7 PocketQubes on top of one of these guys, Electron from Rocket Lab. So yeah, that's the game plan. We want to get the community flying. We want to do it regularly. We want to do it at a price point that makes sense for PocketQubes and is part of the ethos of the community. And we think it's doable. We've actually got about 15 employees at Alpha. Our constant number is a little low. We've been up to about 20. We had a lot of interns over the summer, so we're really trying to make it happen. You know, we're trying to get these workshops going regularly. So the plan is hopefully we can host it annually now and get it going so everyone knows this is the place to come. Got the exhibits, got the poster sessions. Yeah. Go. So any questions? All good. Questions. Cool. All right. Cool. That's good. He's not like a DJ. Oh. So yeah, I just want to thank everyone for coming along. There's someone in particular I'd like to thank. Iris, you know, we've met, he's been running around with Headless Chicken trying to organise things, and we've got a lot of credit to thank him for his efforts. On behalf of Alpha, thanks very much for your efforts, guys.
Thank you very much.
A round of applause for Iris. We've been on this event for the last 10 weeks, so we really do try to professionalise and guys can really work and flat out, you know, answering emails at crazy times and try and chase people for talks and presentations, and there's a lot of effort goes into running these things that we don't see or acknowledge or live stream live, and guys have done a great job on that. So yeah, so that's pretty much it for this year. Plan is to hopefully host one again this time next year. We'll put out some details online, probably someone will chase you up or hopefully you can come out. I'd like to thank lots of people, obviously thank everyone in the room for coming, so we give yourselves a big round of applause for making the effort. That was really great. So. Got a long list of people to thank on the sponsorship side. So we've got obviously Alba sponsoring the event, Skyfox Labs, so they're sponsoring the live stream. They couldn't be here this year. Yaroslav's been to the previous 2 events. He's knee deep in customer problems or customer challenges, so he can make it out from Czech Republic this year, but he's been sponsoring live stream. So we give Yaroslav a big round of applause for sponsoring live stream. Thank you for watching. So that's very kind of him to do that, especially last minute. I'd like to thank Glasgow Convention Bureau, STFC, Printech, our Argentinian friends. I'm trying to think who else has been exhibiting. DHV, give them a big round of applause. That's really awesome. And obviously, Livestream guys have been doing a great job as well. So thank you very much for all your efforts. That's pretty much everyone. So hopefully we see you guys back here, guys and girls back here next year this time. We'll finalise dates and sort of the venue and stuff. Hopefully, it seems to went fairly well this year. If you have feedback for me or feedback for the company, we will want to run the events in slicker and better, more engaging, and we had a bunch of new ideas to implement this year. Hopefully a bunch of them will work. Just let us know what you think, how you can make the event more awesome and you know, it's bad, and you know, we want to really encourage people to get building, get flying, and do cool stuff in space, and yeah, just want to thank everyone. So, go. All right. Good. That's everybody. Okay, well, thank you very much, and have a safe flight home or a safe trip home. And yeah, we'll be doing the integration on Monday, so we'll be tweeting that out, and really excited for that for the community. And hopefully that'll be the first of many integrations. And yeah, take it easy.